A very warm welcome, Bacho. So today we are starting a brand new unit, Unit 3, Current Electricity. Now don't worry at all. We are going to make this super simple and completely exam safe so you can easily score full marks. Think of it this way. We've already studied what happens when charges are just sitting still, right? Now we're going to see what happens when they start to move.
Okay, so let's start with a simple question, just to get you thinking. I'm sure you've all done this. You walk into a room, you flip a switch, and bam, the bulb lights up instantly. But have you ever stopped to wonder, how? How does it happen so fast? Well, that's exactly what we're going to figure out today.
All right, to understand this, let's use a really common and helpful analogy. Just think of electricity flowing in a wire as being just like water flowing in a pipe. If you can get this one picture in your head, believe me, the rest of the chapter becomes so much easier.
Okay, so first things first, what exactly is electric current? Let's get the main idea, the flow of charge, crystal clear.
So, back to our pipe analogy. Imagine you have a long pipe, and it's already completely full of water, from one end to the other. Now, the moment you turn on the tap, what happens? Water comes out the other end almost instantly, right? You don't have to wait for the water from the tap to travel the entire length of the pipe. Well, a wire is exactly the same. It's not empty. It's already jam-packed with electric charges.
Right, now this is super important for your exam. This is the exact definition from your NCERT textbook, and you should remember it just like this. Charges in motion constitute an electric current. That's it. It's simple, it's precise. Anytime, anywhere you have charges that are moving, not just sitting still, you've got an electric current. And of course, we have a formula for this. The formula for current is I equals Q divided by T. Here, I stands for current, which we measure in amperes, Q is the total charge, measured in coulombs, and T is the time in seconds. So it's really just asking, how much charge is flowing past a certain point every second? Super straightforward. Okay, so we have the big picture. Now, let's dive deeper. Let's zoom right into the wire and see what's actually happening at the microscopic level. What are those little electrons really doing inside? This is the secret life of electrons. So, on the left here, imagine a copper wire just lying on your table. It's not connected to anything. Inside, it's full of free electrons, but they're not sitting still. They are zipping around randomly in all directions, up, down, left, right, like crazy. But the average motion is zero. No net flow means no current. Now, look at the right side. The moment we connect a battery, we create an electric field. This field acts like a gentle but persistent push on all the electrons, making them slowly drift in one direction. So how exactly do they drift? It's a four-step process. First, the electric field gives a little push, a force, to an electron. So naturally, it starts to accelerate. But just as it picks up a little speed, bam, it collides with one of the big fixed positive ions of the metal. After that collision, it kind of loses its forward momentum, and the whole process starts over again. It accelerates, collides, accelerates, collides. This constant start-stop journey results in a steady, very slow, average velocity that we call drift velocity. And this picture shows it perfectly. Look at that solid line. That's the electron's actual path. See how it's completely random and zigzag? It's just bouncing around. But if you look closely at the dotted line, you can see that over time, despite all the chaos, there's a tiny overall shift in one direction. That tiny average movement is the drift we're talking about. And now for the most surprising part. How fast is this drift? You might think it's super fast, but no. The drift velocity is incredibly slow. We're talking about just 1.1 millimeters per second. That's it. I mean, you can walk faster than that. A snail can probably move faster than a single electron drifts in a wire. Let that sink in. Okay, so this idea that the drift speed is super slow, this is where a lot of students get confused. And these confusions are what I call silent killers in exams. So let's clear up the biggest doubts right now so you don't make these common mistakes. So question number 1. This is the big one we started with. If the electrons are drifting so slowly, I mean slower than a snail, why does the bulb light up instantly? Well, the secret is this. It's not the electron that's fast. It's the electric field. The electric field, which is the start-moving signal, travels at almost the speed of light. Remember our water pipe? It's already full. When you turn the tap, you're pushing the water at your end, which pushes the water next to it, and that pushes the next bit, all the way down the line. It's the push that travels fast, not the water molecule itself. Same thing here. The field pushes all the electrons at once.
All right, doubt number 2. From Newton's laws, we know that if you apply a constant force, you should get constant acceleration. The object should get faster and faster. So why don't the electrons just keep accelerating? Why do they settle for this slow, steady drift velocity?
The answer is simple. Collisions. Constant, repeated collisions. Think about trying to run at full speed through a really crowded market. You just can't. You take a few steps, you bump into someone, you slow down, you start again, you bump into someone else. It's the same for the electron. The electric field tries to speed it up, but the collisions with the positive ions keep slowing it down. And this whole process, this opposition to the flow, is exactly what we call electrical resistance.
And the last big misconception. So when the current is flowing, do you picture all the electrons marching neatly in a single file line like soldiers on parade? Is that what's happening?
Absolutely not. That picture is totally wrong. You have to remember 2 things. 1, the electrons already have massive random speeds due to heat. We're talking hundreds of kilometers per second in every possible direction. And 2, the drift velocity is just a tiny, tiny, tiny average shift on top of all that chaos. It's like a huge swarm of buzzing bees that is slowly, as a whole group, drifting to the left.
All right, let's wrap this up. We'll connect what we learned today to the bigger picture of your physics syllabus, and then I'll give you a final exam-safe summary. You see, nothing in physics exists in isolation. It's a story. We started our journey in chapters 1 and 2 with electrostatics, which was all about charges at rest. Now in this chapter, we're looking at what happens when those charges are in steady motion. And guess what's next? In chapter 4, you'll study the magnetic effects created by these moving charges. See? Rest, motion, and then the effects of motion. It all connects beautifully. Okay, so for your final exam summary, here are the 4 points you absolutely must know. Number 1, electric current is simply the rate of flow of charge, I equals Q by T. Number 2, in conductors, this current is because of the very slow drift of free electrons. Number 3, the reason it feels instant is that the electric field that gets them moving is established almost at the speed of light. And finally, number 4, the cause of electrical resistance is nothing but the constant collisions between these drifting electrons and the ions in the conductor. If you remember these 4 points, you are perfectly set for this topic. All the best.